Okay, I think I'm recording here. There we go. We should have a pen. So, balancing chemical equations. It's basically all about, well, the fancy term for it, the scientific term for it, is the law of conservation of mass. Law of conservation of mass is just a scary scientific way of saying stuff, matter, can't disappear into thin air and can't appear out of thin air. That's all it's saying. So before we get into chemical equations, why not, let's think about Oreos. Why not? Cookies. Cookies are a great way to teach chemistry. The basic equation for Oreo cookies is outsides plus some insides make Oreo cookies. Now, right now, in chemistry terms, what I'm saying is one outside plus one inside makes one Oreo. How is it one? Because there's no numbers out in front of any of these. In chemistry, when we write an equation like this is sort of the form of a chemical equation. We write our starting materials, what we call our reactants, on the left-hand side of this arrow right there, and our products, or what we make, on the right-hand side of the arrow. So if I was making Oreos, I would start with some outsides and insides, and I would assemble them, assuming Oreos were self-assembly, which I think would be kind of cool. And then I would make some Oreo cookies. Right now, if there's no numbers written in front of the different reactants or starting materials, or the different products or ending materials, then what I assume is I mean one of each. It's just a little chemistry quirk. If there's no numbers there, we assume it's a 1. So right now what I'm saying is one outside plus one inside makes one Oreo. Now if you think about that for a sec, that's not true, is it? One Oreo cookie, and I'm going to draw here. I'm not good at drawing. So there would be an outside of an Oreo, and then you've got an inside, and then there's another outside. So there's an Oreo cookie. Oreo cookies take 2 outsides and then a single inside to make. So technically right now, this equation for the making of an Oreo cookie is violating the law of the conservation of mass. Because I'm trying to say, by writing the word Oreo, I'm trying to say I've got 2 outsides and an inside. Well, on my starting material side of the equation, my reactant side of the equation, I'm saying I'm starting with 1 outside and 1 inside. Well, that doesn't make a whole Oreo. Where'd the other outside come from? It can't just appear out of thin air. In order to make this true, I need to put a 2 in front of the word outside. 2 outsides plus 1 inside. And I mean, I could write a 1 in front of the word inside here, but in chemistry, we don't. If it's a 1, we just don't write anything. 2 outsides plus 1 inside makes 1 Oreo cookie. That is a balanced equation for the making of an Oreo cookie. It's not violating the law of conservation of mass. I have the same amounts of stuff on the starting material side, the reactant side, the left-hand side of the equation, as I do on the right-hand side of the equation. Now, these numbers out in front in chemistry are called coefficients. And what they do is they represent a ratio. No matter how many Oreo cookies I had, the ratio of outsides to insides is always 2 to 1, isn't it? So what these coefficients out in front, they're saying that the ratio of outsides to insides to Oreo cookies is 2 to 1 to 1. For every 1 Oreo cookie I need to make, I need 2 outsides and 1 inside. If I wanted to make 5 Oreo cookies, I would need 5 insides and 10 outsides. This ratio is always the same. 10 to 5 to 5 is just a multiple of the ratio of 2 to 1 to 1. So chemical equations follow this same thought process. And how I like to balance chemical equations is, with our Oreo example up here, there wasn't a lot to keep track of. There were some outsides and some insides and some Oreos. But when I'm looking at something like this, chemical equation like that, there's a lot of things I need to keep track of here. And so what I like to do is I like to write little tally charts underneath each side of this chemical equation. And the tally charts are made up of the different types of atoms that are involved in the starting materials and the reactants, the left-hand side, and the different types of atoms in the product, the right-hand side, the ending materials. We should have the same kinds of atoms on the left-hand side and the right-hand side of a chemical equation because of the law of conservation of mass. If we're starting with carbon, we better have some carbon in the end, right? It can't disappear into thin air. If we start with some hydrogen, we better have some hydrogen in the end, and so on. So in this case, looking through, both sides have some carbon. There's carbon there and carbon there. Both sides have some hydrogen, hydrogen there and hydrogen there. And both sides have some oxygen there. And then oxygen on the right-hand side is actually coming from 2 spots. So we'll have to keep that in mind. The next thing I like to do is I like to write down how much of each kind of atom I have to start off with. This is an unbalanced chemical equation. So it would be like our Oreo cookie equation up here before we put that 2 in front of the outsides. Now you'll notice we've got these small numbers down here. These are subscript numbers that tell us how many of each kind of atom there are in that molecule. So this C5H10, this is actually an organic compound. This is an organic compound called pentene, just in case you wanted to know. It's an organic compound. It's a hydrocarbon, and it's made up of 5 carbons and 10 hydrogens. And so right now, on the left-hand side of the equation, I have 5 carbons, I have 10 hydrogens, and I have 2 oxygens. On the right-hand side of the equation, let's take a look here. So there's no subscript after the C in the CO2. Again, chemists are lazy. If there's one of something, whether it be in terms of subscripts or in terms of coefficients, we just don't write the number. If it's anything other than 1, we'll write a number. But if it's just 1, we just don't write it. So you would never see something like C1O2. We wouldn't do that. We'd just write CO2. So this means there is 1 carbon on the right-hand side, 2 hydrogens on the right-hand side, and there's 2 oxygens here and then 1 over here. So there's a total of 3 oxygens on the right-hand side. So this is just a current tally of how many of each kind of atom I have on each side of the equation. Now, this isn't balanced because right now, this is actually right now in violation of the law of conservation of mass. I'm trying to say that I started with 5 carbon atoms, and then in the end, I only have 1. Where did the other 4 go? So that's the whole point to balancing. There must be there must be coefficients that need to be in front of some of these chemicals so that I've got the same number of atoms on left and right, so that nothing disappeared into thin air, nothing appeared out of thin air. It all balances out. You might wonder why we can't just go ahead and change these little subscripts. You know, why couldn't I just write C5O2, right? That would take care of the discrepancy with the number of carbons from left to right. The reason we can't do that is because that would actually change the chemical. C5O2 is not the same thing as CO2. That would be, in fact, C5O2 doesn't actually exist, but it would be a completely different chemical than CO2 would be. So we can't ever change the subscripts down here because that would change the chemicals that are there. The only way that we can show that there's more than one of something is what we did up here. We can put numbers out in front, coefficients out in front, that will change the amount of atoms that are there. So if I put a 5, so I'm going to put a cross there, can't do that. If I put a 5 out in front of the CO2, that now means that I have 5 carbons on the right-hand side of the equation. That also changes something else, though, doesn't it? I'm now saying that there are 5 CO2 molecules. So here's what CO2 looks like. There's a CO2 molecule. Originally I had one of them. Now I have 5 of them. So you wouldn't have to do this every time, but this is just for explanatory purposes. If I now have 5 CO2 molecules, not only do I have 5 carbon atoms, that's changed the number of oxygen atoms on the right-hand side, hasn't it? Students do get confused at this point. They sometimes think, do I add 5 and 2 together? Do I multiply? What do I do? Hopefully drawing this out shows you what you should be doing. If I have 5 CO2 molecules, how many oxygen atoms do I have? Well, I can count them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So when you're dealing with a coefficient and a subscript, you're going to multiply those two numbers to get the new number of however many atoms that the type of atom we're talking about. So now on the right-hand side of this equation, we have 5 times 2, which is 10 oxygen atoms, but don't forget about the oxygen atom that comes from water here as well. So now we have 11 oxygen atoms on the right-hand side of the equation. Now you might wonder why I started balancing with carbon. I wouldn't have had to. You can theoretically start balancing with any one of these, carbon, hydrogen, or oxygen. Here's a little trick though. You'll notice when I put this coefficient of 5 in front of the CO2, not only did it change the number of carbons, which is what I was sort of focused on at the moment, but it changed the number of oxygens as well. And that quite often happens when you put coefficients in front of chemical formula. Unless the chemical is just made up of one type of atom, it not only changes what you want to change, but it'll change something else as well. If you see in a chemical equation that you're balancing a type of atom that occurs by itself, whether it's on the right-hand side or left-hand side, leave that type of atom until last. And the reason for that is because then, at the very end, once I get carbon balanced and once I get hydrogen balanced, if the only thing left to balance is oxygen, I can put whatever I need to in front of that O2, whatever coefficient I need to, and that's not going to mess anything else up. If I left, say, hydrogen or carbon to last, then I would have to be putting coefficients in front of other chemicals involved in this equation that may end up messing up something else that I'd already balanced, and then you end up having to go back and forth, and sometimes you do anyway. But this is just a little trick. If you have any kinds of atoms that just occur by themselves, leave those till last. Okay? So I started with carbon. Carbons are now balanced. Let's do hydrogens next. Hydrogens, I have 10 of them currently on the left-hand side, and I have 2 of them currently on the right-hand side. Well, again, I can't change that subscript. All I can do is I can put a coefficient in there to make 10 hydrogens on the right-hand side. Remember, what I need is a coefficient that when multiplied by 2 is going to give me 10. Well, 5. 5 times 2 would be 10 hydrogens. And again, if you're having a hard time visualizing that, you can draw out your water. If I drew, there's what water looks like. If I have 5 of those, my messy drawing here, 4 and 5, I have 5 oxygen atoms, 1, 2, 3, 4, 5, but I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. But by putting that 5 in front of the water, I've now also changed oxygens again, haven't I? Now on the right-hand side, I have 5 times 2, I have 10 oxygens from the CO2, and 5 times 1, 5 oxygens from the H2O. So now I have a total of 15 oxygens on the right-hand side. Well, carbon is balanced, hydrogen is balanced. Let's go ahead and balance oxygen. I need to put some coefficient in there that's going to give me 15 oxygens on the left, because I have 15 oxygens on the right. You might be thinking, somewhere along the line, I remember my textbook or someone telling me that I can only have whole numbers as coefficients, and that is true in the end. 2 times 7 is 14, 2 times 8 is 16. What am I going to multiply by 2 to get 15? Well, I'm going to show you another little trick. There is a number that when multiplied by 2 equals 15. It's not a whole number. It's a decimal number, or a fraction, if you want to think of it that way. It's the decimal 7.5. 2 times 7.5 is 15. If I put 7.5 in here, technically, this is now balanced. I have 5 carbons on each side, 10 hydrogens on each side, and 15 oxygens on each side. Chemists, though, we don't allow decimal numbers or fractional numbers as coefficients. We just don't. So even though technically this is balanced right now as it stands, we need to do something to make all of these coefficients be whole numbers. What we can do is we can multiply all of the coefficients through by 2. Chemical equations are very much like math equations. Whatever I do to one side of a math equation, as long as I do it to the other, then the two sides remain equal. If I had something like 2x equals 10, if I multiply both sides by 2, so times 2 on this side and times 2 on that side, I would get 4x equals 20. The answer to x for both of those is 5. So 2x equals 10, 4x equals 20. I haven't, as long as I do the same thing to both sides of a math equation, I haven't changed the overall answer to the equation. Same thing for chemistry. I can multiply all of these coefficients by whatever factor I want, and as long as I multiply them all by the same factor, this would remain, it would stay balanced. So the smallest factor I can multiply through to get rid of that 0.5 is 2. So 7.5 times 2 is 15. Now remember, we haven't written anything in front of the C5H10. That's fine, but there is a 1 there. So the 1 that's there times 2 would be 2. Do the same thing on the right-hand side. 5 times 2 is 10. 5 times 2 is 10. So the overall balanced equation should be 2 of the C5H10s plus 15 of the O2s should make 10 of the CO2s and 10 of the H2Os. Now, not a bad habit to get into is checking. So this should be balanced. Just to check to make sure, though, what I can do is I can start a brand new little tally down here based on the coefficients that I now have in front of all of these different chemicals. And I should, when I tally the number of different kinds of atoms on each side, they should be the same side to side now. So let's see if that's true. So 2 times 5, I have 10 carbons on the left-hand side. 10 times the 1 that's after the C, so I have 10 carbons on the right-hand side, so that's good. Check. Hydrogens, 2 times 10, so I have 20 hydrogens on the left-hand side. 10 times the 2 after the hydrogen and water, so 10 times 2, 20 hydrogens on the right. Check. 15 times 2, so I have 30 oxygens on the left. And remember, oxygens come from 2 different places on the right, so 10 times 2, I've got 20 oxygens coming from the CO2, plus 10 times the 1 that's after the oxygen in the water, which would be 10 times 1 is 10, so 30 oxygens on the right. Check. So this should be a balanced equation.